Howdy, y'all, and welcome back to another lecture in my series for ASTR 124, Introduction to Observational Techniques. Today, I'm going to be talking about a very specific detector, and that is a charged coupled device. Now, detectors have been a revolutionary instrument, or I should say a vital instrument in astronomical research for a long time. Prior to the advent of photographic plates near the end of the 1800s, astronomers were left with simply drawing what they saw through the eyepiece, which A is rather subjective, and B, because of its subjective nature, you can't really acquire any quantitative data. You can't, for example, determine the brightnesses of things with any sort of precision. You can guesstimate how bright things are in comparison to one another, but that's basically as far as you can get with it. Now, if you'd like to know more about, if you'd like me to talk more about detectors such as photographic plates, photoamplifier tubes, and things of that nature, more legacy tech, I would be happy to do so. But for the purposes of this course, I'm going to be concentrating on the most modern device that is currently being used. If I'm honest, the most modern device is CMOS, but the CCD is a still very common in use. So let's get to it. Let's do that. All right. So, as I said, CCD camera. Now, as it happens, to give you a little bit of trivia, is that the CCD camera was first developed as a computer memory device, but its ability to capture images was quickly realized among the astronomical community, and it has become a mainstay detector for a number of different reasons. The primary of which is that its ability to capture light is more efficient, more effective than a photographic plate and a photomultiplier tube. It has the other advantage over a photomultiplier tube because a photomultiplier tube is effectively a light counter. You can't take images using that tube. So here you have something that is akin to a photographic plate, but is much more efficient to use, much cleaner to use, much safer to use. These are two of the first images, astronomical images taken using a CCD camera. The one on the right is the one that is older. That is, believe it or not, an image of the lunar surface using a camera. And the one it was taken in 1974. The one on the left was taken 2 years later, and I couldn't resist. This is the first CCD image of Uranus, and I'm surprised it took them 2 years to do this, because my inner 5-year-old cannot be denied. As you can see, these are very crude, but they set the stage for the power of the use of CCD cameras. So, how is a CCD camera? What is it in physicality? What is it made of? So, the picture on the left is an SBIG STX 16803 plugged to Santa Barbara instrument group. This is the camera that we use on our 32-inch Geller telescope. The detector itself, the chip onto which light is captured, is that square in the kind of the center of it that has that rainbow sort of sheen on it. That rainbow sheen is due to a coating that helps with narrowing down the wavelengths the camera is sensitive to or detects. Now, I don't know why it is not coming in. Okay. Not entirely certain what happened there, but after a bit of technical difficulty, we're back. Now you can actually see the structure of the chip itself. So what you have is effectively an imaging area, which is subdivided into small squares known as a pixel or picture element or pixel. And it is surrounded by a ceramic package, which basically helps insulate it from electrical noise. You have connection pins, which can connect to gold wires. But really, the thing that you want to focus on is the fact that the chip is subdivided into pixels and that you have this serial register. One of the columns is known as a serial register, and at the one end of it is something called an on chip amplifier. And so, what that does, it converts the electrons that are collected on the chip and um, transforms them into a digital signal that the computer can then interpret. So, how does a CCD actually work? Well, a CCD works based on a principle that Einstein got his Nobel Prize for, and that is the photoelectric effect. Now, an atom, classically speaking, or the Bohr model of the atom, I should say, is thought of, you can think of it as a nucleus. The center of the atom is composed of a combination of protons and neutrons, and that is surrounded by a shells of electrons. Now, each of those electrons is bound to that atom, that nucleus, with a certain amount of energy. If that material is hit with light of a certain energy or greater, then the outermost electron will fly off. For hydrogen, hydrogen is simply a proton with one electron orbiting around it. If you expose a hydrogen atom to 13.7 eV worth of energy or more, then that electron will pop off. Effectively, it will escape the influence of the proton and then be what is known as a free electron. It will fly out into space. Ordinarily, depending on the situation, that free electron may very well be captured by some other element there. So, here's an extra credit question for my class, and I will give you a full credit, full point on your final grade if you can email me the solution of this question, the answer to this question. What is the temperature of a black body where the peak of that black body has an energy of 13.7 eV? So, it's, in a way, what is the temperature of the environment in which the electron or the hydrogen atoms will be what is known as completely ionized? All of the hydrogen gas will be basically a soup of simply protons and free electrons flying around that. If you can give that to me, show all of your work, get that answer to me, I will tack on a full point to your final grade. Basically, I'm doing this because A, I'm a nice dude, and two, I want to see if how many people actually watch this video who are in my class. So, okay, in principle, you have in the CCD, the chip itself, you have a photosensitive region. This is typically composed of silicon or silicon dioxide. That is in between an insulating layer and a bulk silicon substrate. Light can come in, and then you have electrodes, which I'll talk about their function in a moment. CCD cameras can be built in two ways. You have what is known as a front illuminated and a back illuminated. And as the names would imply, that indicates in which direction are the incoming photons. Do the incoming photons come in from the front, meaning do they pass through the electrodes first and then hit the photosensitive region, or they go through the back? With a back illuminated CCD, you no longer have that silicon substrate, and so the photons now immediately hit. The first thing they hit is that photosensitive region, and I'll talk about the benefits of that later on. But effectively, what is going on here is that an incident photon will hit the photosensitive region, silicon dioxide, and some of those electrons will be ionized. Some of those electrons will become free electrons, and those electrodes will create an energy or electric field that captures them, that basically holds them away from the the region itself, and that will so they cannot recombine with the atoms below it, and so you have these free electrons just held within the pixel, and that is what a camera actually counts or collects, is free electrons in this process. So when you take an image of the sky, one thing I don't think I mentioned is part of the construction of a CCD camera is something called a shutter. So for our camera, that is simply a piece of black cloth that slides in and out of, or over and away from the chip itself. So when the shutter is open, the shutter is hidden, the cloth is hidden, like in the image that I showed you. When the shutter is closed, that piece of black cloth covers the CCD detector, so no light from the telescope is striking the camera itself. So if you were to take, say, an exposure of 10 seconds, what that means is that the shutter opens for 10 seconds, light from the telescope is allowed to stream in, hit the detector. Those photons will then excite those silicon dioxide atoms, will pop off those free electrons, which will then get captured by an electric field inside those pixel elements, those pixels. Once that is done, once that 10 seconds is done, the shutter will then move back into place, cutting off all light from the telescope. And so you are left with an array of electrons in these pixels, which is a picture effectively of what the telescope just is looking at. Now, how does that get to the computer? Well, it does this by changing the electric potential across these pixels. By doing that, you can literally move the electrons from one pixel to the next. For a CCD camera, the way that it does this is it moves things basically by rows until the electrons are located, except for the electrons that are located in the serial register. For those, it moves them to the side. It moves them from the left to the right in this case for the output amplifier, which then converts those electrons into a digital signal, which the computer can now recognize. Once those electrons have been counted, all of the electrons above it get shifted down by a row, and that process repeats itself until all of the electrons have been counted, turned into a digital signal that can then be downloaded onto a computer, and you now have yourself an image. What this also means is, and we'll talk more about what is known as dark current uh, in the next lecture when we talk about how, how the images that are actually taken with a CCD, what they are, and how they are used to get rid of artifacts and such. One artifact is known as the dark current. So cameras, are, as I like to say, are stupid. They don't know where the light is coming from that hits the chip. That includes light that is coming from the camera itself. Remember when we talked about light, I talked about this thing called a black body spectrum or a spectral energy distribution. Anything that has a temperature produces light as similar to a black body of that temperature. And that object can produce photons along at many different wavelengths. For example, the camera, we typically keep it cool down to about negative 20, 30 degrees Celsius, depending on the outside ambient temperature. Even still, even with something that cold, it still will produce photons that are in the detectable range of the chip. And so that noise will be accumulated. Those photons will hit, create electrons that have nothing to do with what you're looking at in the sky. They're simply the camera itself. And those will collect over time. You can see this. This is also the case during the download process. So you have the top and you have the bottom. Let's ignore the bottom for a second and just look at the top. This is a profile of the pixel count as a function of distance from the top. And you can see that it is brighter. And so effectively it gets brighter as you get to the edge. Effectively, what you're seeing is the effect of the pixels because these pixels are being the pixels here have electrons in them longer because of this download process. You get an accumulation of dark current over here. Now, this on the bottom here, which is much steeper, that I believe is due to light leakage. So there is a port on the camera or on the telescope that is currently open to the sky. In theory, the tertiary camera should block out that light, but apparently it is not doing a completely adequate job of doing it. It's not a big deal, as I will discuss in a future lecture. This artifact can be eliminated or corrected for in the processing. So, what can a CCD see? Oh, I will need to get rid of my face, unfortunately. Sorry, guys. You're going to have to just look at a slide for now. So, when we talk about a field of view is effectively the angular size on the sky that you can see using a telescope and um, detecting instrument. Typically, that is calculated using eyepieces. For cameras, what is more relevant is something known as the pixel scale. Basically, that is the angular size on the sky represented within 1 pixel. So if you have a pixel scale, our pixel scale here at with our camera is about 0.25 arc seconds per pixel. So what that means is that if you were to measure the angular size on the sky that is providing light to a single pixel, that is 0.25 arc seconds square. So that is one way in which you can determine a limiting resolution. Just by that alone, if there are two objects that are closer together than 0.25 arc seconds, our camera would not be able to identify them as separate objects because all of that light is going to a single pixel. We'll talk about something called Nyquist sampling later on, which is which is essentially a guide that astronomers use to determine whether or not you are you determine the quality of your resolution in a way. But anyway, let's return to pixel scale or plate scale. There are two ways you can calculate this. You can, they're both on the left. The first one will tell you what the pixel scale is in terms of arc seconds per millimeter. So you're looking at if you were to take a linear distance in millimeters across the chip, then calculate that number would tell you how many arc seconds are across that millimeter. The equation is 206,265 divided by the diameter of the telescope in meters times the focal ratio of the telescope. The focal ratio is itself the focal length of the telescope divided by the aperture. That is a unitless quantity. One of the things I remember from grad school is that one of my professors was very adamant that every astronomer needs to know the number 206,265 off the top of their head. That is a number you need to memorize because that is the conversion between 1 radian and that is the conversion between radians and arc seconds. So 1 radian is equal to 206,265 arc seconds. That comes up a lot more frequently than you probably would think, particularly if you're talking about the nitty gritty of observational astronomy. The other way you can calculate it. So the first way is you need to know what it's dependent on the The characteristics of the telescope the camera is attached to. But we're not. But when we look at an image, we're not looking at millimeters. Like when we look at the distance between two stars on an image, we're not measuring that in millimeters. We're measuring that in pixels. We can figure out what the pixel position of one star is relative to another. So the second equation is much more relevant. And this is 265 times mu, which is the pixel size in microns, divided by 1,000 times the focal length of the telescope in millimeters. What this should tell you is that the plate scale and in turn the field of view is very much dependent on the telescope camera combination. So if you were to build a camera, hopefully you're going to build a camera, generally speaking, with a specific goal in mind, a specific science plan that you have in mind. And that is going to require a certain resolution associated with it, more than likely. And so when you are building a camera, you are generally speaking going to be building a camera for a specific telescope in order to achieve the resolution that you want. Cameras, astronomical cameras, particularly research cameras, are not swapped around. They are specifically built for the telescope they are mounted on in almost every case that I can think of. And so those are the two ways that you can determine the plate scale. To get to the um, yeah, to get to the field of view, you simply multiply the plate scale by the number of pixels. So let's imagine we have a camera that is 285 pixels long and 524 pixels high, or wide. We know the pixel scale is 0.4288 arc seconds per pixel. You just simply multiply the pixel scale by the pixels, and voila, you now know the field of view. So if you're using this camera to image something, like my favoriteest nebula, the Orion Nebula, and you center it on the trapezium, the stars in the center that you can see there, here, right there. Then that will tell you just how much of the Orion Nebula you will be able to capture in a single image. For our telescope or a telescope camera combination, our field of view is roughly 25 by 25 arc minutes. So it's similar ish to this one. Again, that is something to keep in mind when you are talking about what type of science you want to do. If you're looking at trying to look at open clusters, for example, and if you're wanting to look at an open cluster like the Pleiades, what that means is if you want to capture all of the stars within the Pleiades, which is a very large angular size, you're going to have to take multiple snapshots using a camera such as this and the 1R telescope. But if you're interested in looking just simply at an exoplanet, then this is far more appropriate. Spectral response. Let's go back to the front and back illuminated CCD. As I mentioned before, the reason for why this was created is because of spectral response. The first CCDs that were created were front illuminated. And the reason for that is that they are easier to manufacture. Back illuminated were created in an attempt to improve something known as the quantum efficiency. Quantum efficiency is the percentage of light collected as compared to the amount of light that hits the camera. So let's say if we look at these curves, let's take this curve right here, this big one. And let's take it here at this particular wavelength, just let's say 550 nanometers. Then the quantum efficiency at that wavelength is 90%. So if you have 100 photons with that wavelength hitting the camera, 90 of them will be counted. The other 10 will basically be reflected off of it or will not be detected effectively. So you can see that this is, and these curves are what is known as the spectral response. It is the quantum efficiency as a function of wavelength. And what we have here is this bottom curve is a typical front illuminated CCD. These are two different types of back illuminated cameras. I can't remember exactly what company these are, but yeah. What you can see, the takeaway point here is that the quantum efficiency of a back illuminated chip is, generally speaking, 2 or 3 times better than that of a front illuminated chip. The other thing that you may notice is that a front illuminated chip tends to be more responsive or have a higher quantum efficiency over to the right, basically in the red. For some back illuminated, there's a tendency for them to be uh, more sensitive to the blue and to the ultraviolet, near ultraviolet, and the blue. For our camera, it's actually about flat and it's towards the red. So if you were looking in the V band or the green light, all the way through to red, all the way through to infrared, the quantum efficiency is roughly about 80% or so, 80, 90% or so. It drops off precipitously when you go into the blue. So blue, that's about the quantum efficiency there is uh, basically slightly over 50%. The quantum efficiency in the U band is a little bit more than 25%. So this is something that you want to keep in mind because that is going to dictate how long you need to collect light in order to get enough signal for it to be useful from a data analytics point of view. Aha, I'm back. Next thing you need to know is something known as linearity. So this is taken from Kodrick Observatory. This is apparently actual data, and it's a little bit kludgy, but I wanted to show you an actual data as opposed to a representative curve. And what they've done here is they've looked at presumably a particular star, and they've taken multiple images of that star with varying exposure times. And so for example, when they look at the number of counts, the mean counts of a star for at 1 second, then the number of counts that they get is around 15,000. They double that. And then they increase the exposure time. That collects more light, and so the number of counts goes higher. Now, for the most part, one of the advantages of a CCD camera over, say, a photographic plate is that for the vast majority of counts within the pixels, it's a linear relationship, meaning that if you double the no, double the exposure time, you get twice as many counts. So here this is, like I said, this is where it gets a little bit kludgy. I don't know if this is some sort of systematic error in their camera or what have you, but effectively, um, you go from 15,000 counts at 1 second. At 2 seconds, you get up to 30,000 counts, and so forth. This is vital if you want to be able to do differential photometry. Differential photometry is the process via which you compare one magnitude or the counts from one star to another. If this correlate or if this linearity does not hold, if you are in the non-linear regime, then you're not comparing apples to apples. So the relationship between the number of counts and the magnitude of that star will not be the same for these two stars. And so therefore you cannot, or it would be very inappropriate to try to do differential photometry between the two. So in this case, the linear regime is approximately from about, I don't know, I would say 0.5 seconds to roughly 3.5 seconds. On the short end, you start dealing with such effects of uh, detector noise, that sort of thing. But over here, what you see with cameras is that when you get closer and closer to the limit, which I'll talk about in a second, you find that the relationship between the exposure time and the number of counts you get falls off and is no longer a straight line. It basically curves downward, so that when you increase the exposure time, you're not getting nearly as many counts as you would if it were linear. And so this is one of the reasons why you do not want to uh, get a lot of counts on your targets. Now, let's talk about dynamic range. Dynamic range and well depth. Well, first, let's talk about well depth. Well depth is the physical capacity for the pixel to hold electrons. Effectively, there is only so many electrons that that pixel can hold before it becomes saturated. What that means is that if you were to throw more light at that pixel, no more electrons could be freed up and captured by that electric field. For the CCD camera, for our CCD camera, the well depth is about 100,000 electrons, or as it translates with our particular camera, that's around 65,000 counts. So that's how. So you have that signal or that amplifier. Actually, it's called a digital to analog to digital unit converter that converts electrons into counts. So for our well depth, that means that no matter how much light you throw at it, if you get to that depth, you're not getting an accurate measure of the star, because you are not getting an accurate measure of the number of photons that are hitting the detector, and you're not getting a number of counts, and that leads to something on the left over here. Over here, you have what is known as blooming. You get these nice diffraction spikes. From a science standpoint, there you can't do anything with this. You can't get any data or you cannot use this for any relevant data. You need to have you need to basically, in this case, you need to lower your exposure time so that you have less counts, so that you can get a solid definitive number of electrons that are produced. So that's another reason why you don't want to take a really long exposure on a really bright object. So the first thing is you're probably going to be in the nonlinear regime, which makes the observations fairly useless. And then in the extreme case, you're saturating the chip, which again makes the observation useless. That is different from what is known as the dynamic range. The dynamic range is effectively what I would refer to as the brightness contrast. It is the range between the full well capacity, the saturating limit of the camera, to the noise floor along with the sky brightness. So if you're just talking about the camera itself, then you're just talking about the noise associated with the camera, which is the dark noise and the read noise. The number of pixels or the number of electrons from that is going to be your dynamic range. Now, in practice, the apparent dynamic range is also going to be limited to the background sky. The background sky is lit up. It does have a brightness to it, and so it's going to have photons from that sky brightness that is due to light pollution and just background objects that are so diffuse that you don't even recognize them as objects, but primarily light pollution. That means that you only have a certain amount of range to capture good data or usable data on a dim object and a bright object within the same field of view. So if you exceed that range, you have two options. You're going to either not see the dim star if you want to see the bright star. If you want to see the dim star, then that means you have to saturate the bright star. So if the brightnesses of these two objects are beyond the CCD's dynamic range, then you cannot get good data on both objects at the same time in the same image. This is where the eye is better than the camera. The dynamic range of the eye is far better than the dynamic range of typical CCDs to date. And that's basically the only thing that it's better at doing, or the most important thing. Finally, let's talk about noise. This is the ye old CCD equation. This will be the last thing I talk about. So this equation talks about signal to noise. What that means is, as as the ratio implies, that is the amount of signal that you get from a target object divided by the amount of noise that you get from that same object due to various effects from the camera, from the sky, and actually from the star itself. All of these contribute to noise, which is which will degrade the quality of your measurements. As a rule, I generally will say that data is reliable if the signal to noise is 100 at least. That means for every 100 counts, for example, I only have one count that is noise and is not representative of the target object. Signal to noise of 10 means that I only have 10 counts relative to a single count of noise. And then a signal noise of one is one count of signal as opposed to one count of noise. At that point, you cannot tell the difference between what is astrophysical and what is just noise, error essentially. So signal to noise is very closely related to error. The higher the signal to noise, the smaller your error bars are going to be, the more confident you can be in the measurements that you take using the camera. So just to run through this, n star is the number of photons collected from the target. We'll talk about aperture photometry in the next lecture, and I'll talk about how that number is collected. N star is not the number of photons from your target specifically. It is the number of photon or number of counts that are in the area of your target star, for example. This includes the brightness of the sky as well. So you're getting a contribution from the sky as well. So n star is the total number of photons you measure, or counts that you measure. N pix is the number of pixels that image or that target moves or covers. In the last lecture in class, I talked about a PSF, or point spread function. A point source like a star is going to be blurred over a certain area. And for a CCD camera, that means that area, that blurring is going to be over a certain collection of pixels. And S is, I forgot to put that in. NS is the basically the number of photons you get from the sky. So that is a sky brightness. That is photons per pixel, or counts per pixel. ND is the dark current, which in this case is simply the electrons per pixel. So what is implied in here is an exposure time. So this is a function of just a single image. If you increase the exposure time, as I've mentioned before, you get more light. So the number of photons in n star is going to be larger. And so that is the best way to increase your signal to noise. Dark current is going to be a constant value at a particular integration time. In reality, dark current is in a way, it's kind of a velocity. It's the number of electrons per pixel per second. So in this case, for our camera, that is by spec 3, meaning that if I take a 1 second exposure with our camera and I look at each pixel, 3 of those electrons contained within that pixel came from the camera and not from the sky. So if I expose for 2 seconds, then it's 6 electrons. It's a linear relationship. And then you get read noise. Read noise is the random fluctuations within the pixel as it's being downloaded and read by the converter effectively. And in this case, you have for our camera, it's 9 electrons. So basically, that's your error bar. That contributes to the error bar. So if we're just looking at the error coming off of reading reading a pixel, just from the read noise, say I measure 1,000 electrons in a particular pixel, that is plus or minus 9. I cannot know that number more precisely than 9. That contributes to the overall error budget as described by this equation. All right, I believe that is all I have. So, um, yeah, like I said a couple of times, the next lecture will be on. You know what? I think I misspoke. The next lecture will cover CCD calibration. Effectively, what are the types of images that you need to collect in order to eliminate those sources of noise, or rather mitigate the sources of noise that are located in that equation. So, and those are science images, dark currents, flats, biases, that sort of thing. So the next lecture will definitely talk about that. I think the lecture after that is actually going to talk about how we extract data from the CCD camera. Okay. And just as a note, remind you, I did offer that extra credit point. If anyone who is not in my class wants to give a try at it, please email me at parksj762@gmail.com, and I'll look at it and see. I'll let you know if you got it right, and if not, I'll let you know where you went wrong. I hope you learned something, and I also hope that you found this entertaining in some way or another. All right, till next time. Peace out. Clear skies.